so let g of x equal this for x greater than 0. Identify the x value of the critical point. Identify the x value of the critical point of g of x. X value of the critical point of g of x, and classify the point as relative to max, min, or neither. So what should we do to find critical points? Just the first derivative, set it equal to 0, no? First derivative, so g prime of x and 4x minus the derivative of ln x is 1 over x equal to 0. So how do we solve this? Maybe, what do we do? Move this over to the other side. 4x equal 1 over x, and cross multiply maybe. So 4x equal positive 1 over x, cross multiply. So we'll get 4x squared. 4x squared equal to 1. Divide by 4. X squared equal 1/4. Square root it. X equals plus or minus 1/2. And so, what? The only critical point would be what? The positive 1/2, because of x is greater than 0. For x is greater than 0. So we're only going to use, we're going to test x equals positive 1/2. Classify the point as relative max or min. The last lesson was about taking the derivative again and see if it's concave down or concave up. Why don't we do that? By doing it that way, or we could also just test this one, no? Which one is better? Whatever, no? If we do take the derivative and test this point, g double prime of x is going to equal to, g double prime of x is going to equal to 4. All right, 4. And then we got this minus 1 over x, minus 1 over x. So what's the derivative of this? That would be also what? We have a negative x to a negative 1. And then take the derivative of that. Bring it to the top. Take the derivative of that. That would make it a positive. Positive. And then what? Minus 2. So it would be plus what? 1 over x squared. So what now? What do we do? Set equal to 0, so what do we do? Oh, plug it in, huh? Just plug in x equals 1/2. See what g double prime or 1/2. 4 plus 1 over x is 1/2 squared. Why did I even say equal to 0? Why did I do that? All right, so we just want to know if it's a positive or negative for concavity. So that's going to be what? 4 plus, it's positive. It's going to be positive because this thing is going to be positive. It's positive. So it's positive, which is concave up or concave down? Concave up. So it's concave up. So it must be a minimum, no? Let's see. So identify that x equals 1/2 is the only critical x value in the domain. Plug it in to see what sign it is. If it's a positive sign, is concave up. So G has a relative min at x equals 1/2 by the second derivative test, because G double prime of 1/2 is greater than 0. And we've already said that this is the only critical point because of G prime at 1/2 is 0. Okay, so let's go to sketching graphs of functions and their derivatives. Okay, this is redundant, keep stating it, keep saying it, but this is the most important thing, is that what are derivatives? What are they? The first derivative of a function f gives the of f at any x value. Gives the what of f? F prime gives the what of f? The slope, the rate of change of f. So f prime gives the rate of change of f, and the rate of change is slope. When the rate of change is greater than 0, when f prime is greater than 0, is the slopes of f are what? When f prime is greater than 0, so you got some function and the slopes are greater than 0, because the slopes are positive, then f must be what? Let's see, let's go with the same color. This is f, and this is f prime. So when it's supposed to be tangent, so when the slopes are positive, when f prime is positive, the slopes of f, when f prime is good, the slopes of f are what? The slopes of f are what? The slopes of f are what? What is that missing there? Positive. It's talking about slopes of f are positive. Or if it didn't say that, then it would say the f is increasing, but it's not. It's talking about slopes. So it's positive. Positive should be. If it would have said, when f prime is greater than 0, f is increasing. That's another way. F is increasing. When f prime is less than 0, the slopes of f are negative. F is decreasing. And the second derivative, f double prime, of a function f gives the of f at any x value. The second derivative of f gives of f at any x value. What is it missing? What do you guys think? The second derivative of f gives that of f. What does the second derivative give you? Acceleration, yes. But another way of looking at it or saying this is that, like I said, we were looking at f, and we're saying that f prime is f prime is the slopes. F prime is the slopes. F double prime would give you the concavity of it. So we're talking about what are the slopes doing. So concavity gives you about what the slopes are doing. And if it's doing this, then we're talking about gives the rate of change of the slope of f. The rate of change of the slope. So we're describing the rate of change of the slopes of f. So when f double prime is greater than 0, when f double prime is then we're talking about concavity. When f double prime is greater than 0, it's concave up. The slopes of f are, when f double prime is greater than 0, concave up. What are the slopes of f doing? What are the slopes doing? The slopes are increasing. F is what? What do I have? F is what? Concave up. F is concave up. When f double prime is less than 0, that's concave down, and the slopes are decreasing. The slopes of f are decreasing. F is concave down. Alright, so let's go to this. Graphing f prime of x. Given the graph of f of x. So this is the graph of f of x. We're going to focus on the blank of f. The blank of f is the blank of f prime. Okay. So on the same graph of f, we are going to graph f prime of x. So let's graph f prime of x here on the same graph of f. Let's use the, oh no, undo. Let's use this color better. F prime of x stands up. Alright. So it says to focus on the of f. Focus on the slope of f. Slopes. Focus on the slopes of f at every point. The slopes of f r is, or the slope of f is the y value of f prime. So here's the connection. So for f, this at this point, the slope is what? What slope here?
0.
So then the rate of change is 0 here, then it would be for this one. For f prime, it would be here. It would be 0. As the same for here, the slope is 0 here, so it would be, for this one would be there. So yeah, we got these points for f prime. Okay, what else? If I focus on any point on this side here, say at this point, the slope is what? What is the slope? Positive. The higher it is, like that's the rise over run is rise is going to be 1, 2, 3, 4, 5, and then over 1 is more than when it's less like this. See, rise over run will be less, no? 1, 2, and then so the higher it is, the more tilted it is, then the bigger the rate of change. The bigger the rate of change. So it's just it's a big rate of change. It's somewhere up here. But then the rate of change is getting less. This one was higher, then it's getting less, and it's getting less until it reaches 0. So it's getting less, and it's getting less, it's getting less until it's reaching 0, the slope of 0. Here, the slope is what? The slope is positive or negative? So it's going to be somewhere down here until it reaches a inflection point, because this one is negative, but then it didn't want to keep going negative. It turned around to becoming positive, it was going negative, and then said, stop, and then start going. So this is an inflection point, say here. An inflection point, and then so that one is going to be an inflection point. Let's see, it's still negative. It's still negative down here somewhere. Then it's turning around to becoming closer to positive, so it's going to go back up to the top. And then these are positive slopes. So the graph would probably look something like this, of the derivative of f. So a good connection here, a good thing to know about what this is from pre-calculus, is that if you have a third degree function, which this looks to be a third degree function, so if f of x is some third degree function, whatever, let's just say it's x to the third, what is the derivative of f of this one? What would be the derivative of f of x? What's the derivative of this? Say this, no? What's the derivative of this? Which is what? It's a what? A parabola. It makes sense. So if you have a third degree, the derivative of a third degree would become a parabola. And so if you have some fourth degree, say instead of having something like this, and you had a fourth degree, that the derivative of a fourth degree gives you a third degree. Some third degree, whatever this number, the constant is. Okay, so let's do one more. Graphing f of x given the graph of f double prime. We're going to go backwards. What if you have the derivative graph? If you have the derivative graph So we want to know where did it come from. So it must be some, like I said, this looks to be a third degree function. What should its f function, what should f look like? Like, look, you guys remember, no? You guys can, we said that a first degree is a line. A second degree is a parabola. A third degree, like a sideways S. A fourth degree, like a W. So, if you take a derivative, of a fourth degree, you get a third degree, which is this. So what we're looking for is a fourth degree, some W looking thing. So, okay, so what are we going to do now? Graphing f of x given the graph of f prime of x. But when you take the derivative of something that we're saying it was some fourth degree, so say f of x was some fourth degree. Say it was a fourth degree. We will have lost the constant. So this constant, say, is some constant, some number. I could even put a number for it, no? What, 5? So if I do take a derivative of f, then I'm going to get f prime of x would be this. And it would be some third degree, no? 4x to the third, whatever, if it was this. And then the constant would be gone, because the derivative of 5 is 0. So when you're trying to draw its antiderivative, or it's called antiderivative, then we don't know where exactly on the graph it is at, but because it's the vertical shift of it. But in any case, how can we go off of where's the point? How can we graph this? Graphing f is given the graph of f prime of x. F prime of x. What is this? The rate of change is what? Because this is f prime of x, no? The rate of change is what here?
0.
So what now? The rate of change is 0. What does that give you? What does it tell you about graph of f? Of f? Oh, a horizontal tangent. That f has a slope of 0 here, and f has a slope of 0 here, and f has a slope of 0 here. But then how can we start putting it somewhere as a reference? Where do I put it? Because we lost the constant, you're just gonna have to just. What does this one give you? What does this one give you? What does it give you? An inflection point, no? A point of inflection is correct, no? So that's an inflection point here, and this is an inflection point here, no? So these are inflection points. These are inflection points. Inflection points, no? What do we say? So we're saying it's a W, no? It's a W. So where is an inflection point here? An inflection point would be where the concave up meets the concave down. So it'll be somewhere there, and then from this concave down to concave up would be there. All right. So these would be inflection points. What are we gonna do? I don't know. Let's write an inflection point. Let's draw an inflection point there. Somewhere. You have to draw it somewhere. There's an inflection point. Are we going to do it there or there? Where are we going to put the inflection point? Let's put it there. So the graph is concave up here, concave up. How are we going to go about drawing this? Anybody? How are we gonna? How can we? So what? We're here that it is an inflection point, and should it go up or should it be going down? At this left inflection point. So we're trying to draw something like this. So let's say that this is the left inflection point and the right inflection point, left and right. So we're trying to get this is concave up. The slopes are what here? What are the slopes doing here? They're decreasing, aren't they? The slopes are decreasing of this is, but this is f prime. This is f prime, not f. How are we going to draw this? So basically, you want to draw this, and how do we draw it? That's an inflection point. What I'm going to do is I'm trying to just draw this. And that's an inflection point. And I'm going to do this. The slopes are 0, you said, huh? The slopes are 0? So wouldn't it be have a 0 slope? Yes. So it would turn here. And then have an inflection point closer to over here, where it changes there. And until it has a slope of 0. Somewhere here maybe. You'll have a change. So all we do know is these inflection points, which would be this inflection point. That's all we know. That is an inflection point. That is at the slope is 0, and that is at the slope is 0. Let's see. So how can we go about doing this? It was so like we're like, where do you start? So this is telling you, plot the minimum and the maximum points first. So where's the minimum points? Plot the minimum and the max points. Where would be the minimum at? How do you know? Where's the minimum at? Oh, if this is f, how would you know that's the min and the max? Where's the min? Where's the min? Where would be a min? Where's the min? If this is the derivative, the velocity, where would be the min? What is it doing here? What is f doing? What is f doing? Say this point. What is f doing? It's going. It's decreasing. So this would be a what? What would this be? What would this be? A min or a max? Decreasing. It's going from decreasing to going on. So that's a min. Why don't we go like that's a min? Let's identify the mins and the max then. So when you're given f prime of x, identify the min and the max. So that is a min. What is this?
Max.
And then what is this? A min. So that should be a min. So if that is a min, and that's also a min, then let's put a min. Let's just kind of move it and say that it's right here. That's a min. For f, we're talking about f. It's a min here. And a max for f, let's put it somewhere here again. It's just relative. We don't know. And then a min, another min. We got another min. Put it somewhere here. I don't know. Somewhere here. And it says use the inflection points for concavity. An inflection point is, where's the inflection point? Where was the inflection point? We already, you identified it already? Isn't this an inflection point? And this is an inflection point? And then just kind of connect the dots, I guess, all the way to there and there and there and there. Connect the dots. In any case, oh, and then what do we do here? That's a max. That's a min. If that's a min, then it had better turn around. If this a min. If that's a min, better turn around. Yep. So it's a 4th degree. All right. Hopefully this somewhat makes sense. This is one of the weirdest ones to kind of go over. Let's finish off with number 3, and that will be it for today. The graph of f prime of x is shown, and it is known that f of 0 is 0. Which of the following could be the graph of f of x? The graph of f prime of x is given. F prime, the derivative. So, I don't know, you guys copy it. Let's just talk about it already. What do we look for when given the derivative graph? What should we look for? Mins and max? Mins and max? So where's the min? Because you're going from negative to positive, from negative to positive, that's a min. That's a min. Min. And this is going to be a, because going from positive to negative, it's a max. So add 2 should have a max. If this is f, because we're looking for f, this is f, this is f, this is f. Add 2, so whatever, it should have a max. Maybe that one. No. Maybe. So it could be this, could be this. Min has a min at 3. Not really, it's kind of messed up. Has to be this one. F of 0 is 0. F of 0 is 0. F of 0 is 0. So they all could be. That doesn't even give anything away. So it has to be one of these. What else can we use? At what was that? Slope is 0 here at 1. 1. The slope is 0. That's an inflection point. No? Yes. Inflection point from inflection point at 1. There's no inflection. Okay, I guess this is concave up, and it's supposed to be concave down, because where this has all no concavity, it's C, I guess. Let's go. I think it's C. C. I mean, these not exact. I drew them. They're all messed up.